So, good evening all. This will be final session, and this is more like an extra session. So I will be going through all the sessions that have been discussed before. I'm not going to tell every part, but I'm going to just give a brief revision so that it might be helpful for your NPTEL exam uh, recent. So yeah, it will be 2 hour session. I hope I will complete everything in 2 hours, which is again not possible, but I will try my best to complete everything to session 12 what I have discussed. Right, so yeah, so first session, it started with more or less the phase equilibria, right? So in phase equilibria we discussed uh, more about, like, how the phase remains stable. So how any phase will remain at a certain state, right? For example, uh, I even have discussed before what exactly is a phase. So phase is nothing but it is a separated homogeneous system, separated system which has a certain boundary around it, right? A certain boundary around it, and it is separated from the environment, or you can say we have system and surroundings. So surroundings are separated from surroundings, and within that phase, it is chemically homogeneous, right? That means if I try to find anything, right, it will be same. For example, if I have one atom here, then it will be one atom there. So if I have carbon here, then it will be carbon there. So everything will be same throughout the system, right? So that is about phase. Now that is about chemical homogeneity, right? Chemical homogeneity, chemical part. Now second one is it should be physically distinct. So these two are important, right? So mechanically it may be separable or not. It depends upon other things, right? So let me change the audio settings. It's better. Yeah. So these two are important. One is chemically homogeneous. Right. So we have one more slide here. So it should be chemically homogeneous throughout the system. Chemically homogeneous. And the other thing is should physically distinct. And the third one is mechanically separable. So which is not possible for these cases, right? This case might be possible or might not. It depends upon um, the type of system we are choosing, right? So we cannot say that these two conditions may not hold for many of the systems, but the one thing that should hold is the chemical homogeneity. So for example, if this is my system, and if suppose if I have NaCl here, right? So Na and Cl, Na is bonded to Cl, and the coordination number might change, right? It might not be the coordination number might not be the same one, right? So for example, if Na is there, so we know NaCl is an FCC crystal structure. NaCl forms an FCC crystal structure. So either Na or Cl might take the corner atoms, right? So let's say if Cl minus takes the corner atoms, then Na will sit here. So what are these called? These are called the octahedral voids. I have discussed this, so I'm just pushing it. These are the octahedral voids, right? So Cl sits there. Now moving to, yeah, so for example, if this is my system, then everywhere I see it should be an NAC, right, throughout the system. That is what we mean by the chemical homogeneity. So when we are talking about phase, the one thing that should come in mind is the chemical homogeneity, right? It may not be physically distinct. For example, it depends on what type of sensing media we are using. For example, in spinodal decomposition, which I have discussed in session 12, right? In spinodal decomposition, if you have two phases, they might be same. They might look same, right? For example, I might have, how should I say, my sensing media is light. So under photons, it might look the same, but if I am using electrons, and the electrons, the signal is my BSC, back scattered electrons, then my physical distinction can be made, which might be not possible for SC and for photons, right? So that is now that is about phase. Now moving on to FCC. So I have said there are two basic types. There are different types of crystal structure. There are 7 crystal structures and 14 Bravais lattices. Right. There are 7 type of crystal structures and 14 Bravais lattices. Right. Now, the next thing is, and the most basic form we have seen or we have discussed, or right. So there are 7 crystal systems, and I have even mentioned before. It will start with triclinic, monoclinic, then we have orthorhombic, triclinic, monoclinic, orthorhombic, hexagonal, or I should say trigonal, rhombohedral, so we call rhombohedral too, and then I have what do you call tetragonal, and then I have hexagonal, and then I have cubic. So these are my 7 crystal systems, and according to them I have 14 Bravais lattices. So what is the Bravais lattice? So if I try to arrange the dots or points in a 3-dimensional space, the maximum combination I can get is 14 times. That's it. That's the maximum number of combination if I try to arrange the dots in space. Right, so I have discussed FCC and I have phase center, right? So this is like this. The phase center lie here, atoms lie here, and there are corner atoms, and then I have phase center, right, for every phase center. In the BCC, again the same. I have the corner atoms, but I have only atom at the center. That is what we have discussed here. And after that, we have discussed what exactly are grains. So grains are, again, I have said it many times, grains are nothing but inside the grains I have a single orientation of atomic planes, right? For example, this is like this. These are my array of atoms. Atom sits at the intersection points, and suppose this is my 111 plane, and this is suppose the gamma austenite. Then the other grain gamma 1 and this is gamma 2, and this has a little different direction, right? It is rotated. Okay, so if I try to draw, so it will look like this. This gamma 2 and this is gamma 1, and these have the angle relation. And there are different types of these. Will come in a bit. After that, we understand why we need the phase transformation, right? So our main topic here, the topic of the session is the phase transformation. in materials, of course. So how phase transform inside the material, and indirectly it is going to grains. If you're talking about solids, if you're talking about liquid, it is solidification. Right. Now, again we have discussed what are the phase properties, right? Separate entity, followed by again we have direct definitions. Then again, how do you know which phase is stable? Right. So phase stability is given by G. Now again, the arrangement of atoms. So difference between two phases. So for example, if it is a A phase has converted into B phase, and we didn't add anything, like we didn't change any chemical homogeneity, we just increased the temperature or we decrease the temperature. So A transformed to B. What that means? The difference is only the arrangement of atoms. Arrangement of atoms. Because of the arrangement of atoms difference, the phase A is different from phase B. So let's say is A type of arrangement and B type of arrangement. Then we have let's suppose B is at lower state, A is at higher state. That's why the system is trying to move from here to here. But it is not that straightforward. Right? So it is more or less looks like this. So this is the energy difference. Now this is the energy we need to supply so that the system can transform easily from state 1 to state 2. It is also known as activation energy. So that is about free energy state. Again, it is the dependence on energy states. So this is my this is my minima, and this is also minima. But this one, again going on, this is also minima and this is also a minima. This is my maximum, right? So this is minima 1 and this is minima 2. What is the difference between them? The difference between them, only the difference between is this is a local equilibrium, local minima. What is the global minimum? So locally, if I see here, if my only site is here, and if locally it is minima, but this one is my global minimum, because if I have a site of the whole system, then what is the lowest point? This is the lowest point. So that's why we call it as global minimum. Right, now that is about global minima and right now is about the energy of states, and then we have arrived. So how do we calculate this famous equation G equals to H minus Ts? Right, this is the free energy, this is the total energy of the system, this is the unavailable energy. So this amount of energy is not coming, whatever we do. It is going to use in some arrangement of the system. Right, forget about it. I'm not going to use this energy. Right. So now how do we calculate this? Can we calculate this? Okay, let's see. So H equals to dH is equals to NCP dt. So what is Cp? It is specific heat capacity. Now what is specific heat capacity? It is the amount of heat required to rise. So it is simple. So for example, you have a system. So it is at 25 degrees centigrade. Now if I raise it the temperature to 26 degrees centigrade, same system, we didn't do anything, everything is same. We didn't even increase its size or anything, just the same system, right? So it is S1, then it is also an S1. So what we did, we tried to increase the temperature. of the system from 25 to 26. So there is 1 degree change, right? So that is the difference, 1 degree change. And also let's say it is 1 gram. Now what is the amount of heat energy that we given to this system such that it changed its temperature from 25 to 26. So in layman terms, it is the amount of heat that is required to raise the temperature of a system, to raise the temperature of 1 gram of a system through unit degree centigrade. That's it. Now that is NCP dt. Now Cp may vary with temperature or it may not vary. So that's why we have a relation. Either you have A constant, or either you have this guy relation, or you have this relation, or even you have this guy. So it depends upon how my, if I try to draw Cp with respect to the temperature, how does my curve looks like? So it may be linear fit, it may be constant first of all. So this is my Cp, this is my temperature. First of all, it may be constant, or it may be a straight line, or it may be a parabola or hyperbola, or it might something look like this. We do not know. It depends upon the material. Right? It is a material property. So these are three different types. So these are the equations. Right, so these are the three different equations we arrived now, from which you calculate Cp, and we also know what is delta S equals to del Q upon T, and what is del Q, and Cp dt upon T. Again you have a relation, so you do the integration and you will have the delta S, from which you will get delta G. Or we know, so I have derived this relation many times, right? So delta G equals to what? VdP minus SdT. I'm not going to derive. I have derived this many times, so you can directly use it. If you know the change in pressure, you know the change in temperatures, and you insert these values here, you do the integration, and you have the delta G. That's all. Now, after that, we discuss what is the first law of thermodynamics. The zeroth law of thermodynamics, which tells about the temperature equilibrium, right? From that we came to first law of thermodynamics, which gives the energy work conversion, right? So energy work conversion, that tells me about the first law of thermodynamics, right? After that we had second law of thermodynamics, which tells you what is the extent of work being converted, and third law of thermodynamics tells some part of the work is not being used. So what is that work? It is entropy. That's all. That's all. That is the total thermodynamics. But you know, when you go deep into it, it gets more complex and complex and complex. Right. So that is all about thermodynamics. Then we have how the H. Yeah. See, the H versus temperature, S versus temperature. If I multiply to minus, it will change. There will direction change. Then G equals to H minus Ts. You will get G. See how derived this VdP minus SdT. Then you have the Cp measurement. Right? How do we measure the Cp? Again, if you want to know the difference between two states, right? So I have state 1 and state 2. What is the difference between them at a given temperature? What do you do? H2 minus H1, H2 minus H1. Solve. So this is how the delta G for solidification comes, and this is the phase equilibrium, right? The mechanical equilibrium. From this we derived the famous one, this guy, right? from statistical entropy, we arrive to the delta S equation, which we have used many times in this session. X ln x plus x ln x. Right. Then again, the G final is equal to G initial plus delta G mixer. It is just a final. We did finding for G final. What is the final free energy, right? What is the final free energy of the system when it undergoes any transformation? And it is also, we assume it is an ideal solution. So delta H mix is 0. There is no heat released or there is no heat absorption. Yeah. Then we came to represent what is the chemical potential. Right, so again, chemical potential here. So we came to know how this equation equals to chemical potential. Then we tried to know what are the number of tetrahedral voids, or then how many there are octahedral voids. Same here, we tried to know for BCC and FCC. And this is for like a parabola and hyperbola. As I have mentioned before in spinodal decomposition also, the G versus X curve, right? G versus X curve mostly look like this, not this. It's not a hyperbola, because hyperbola has two foci, right? And the parabola has only one foci. So please remember that. Yeah, that's all. Yeah, again, this is like oxidation reduction. Fe is getting reduced, right? Because the Fe has +3 state here, and it is going into pure iron. So Fe has elemental iron, which has 0 oxidation state. So it is undergoing reduction. Whereas aluminium is Al, and it has gone into Al+3. It undergoes oxidation. Again, in first law of thermodynamics, we have seen like Q equals to W, right? And there comes a term like internal energy. Q equals to delta U plus W, right? And how this term came? The delta and delta U term came because even if you do not give energy to the system, right? If you just apply work, you will get some energy, right? If you give some energy, the system will do some work, right? Now, what happens if we do not give the energy to the system? If we only do work, then what happens? Does it release heat? How does it release heat? So it comes from the internal energy of the system. That's all. So that's why the internal energy term is invented. And the same goes for the second law of thermodynamics. What does the second law of thermodynamics says? Second law of thermodynamics says what is the extent you can convert, right? So again, why internal energy was invented? Internal energy was invented to quantify the total energy of the system, right? Including the microscopic components like kinetic energy, potential energy, like there are many things. Like internal energy represents okay. Right, so now that is about that. Now moving on to session 2. Session 2. Yeah. Again, we have derived here the same thing, that dg equals to vdp minus sdt, right? So how do we arrive from that? So g equals to h minus ts, and dg equals to d of h minus ts, and dg equals to dh minus. So if I do the differentiation, so it will be by differentiation by parts. dt times s plus tds, so dh minus sdt minus tds. So dg equals to, again, we know enthalpy equals to internal energy plus p beta. This is the total energy of the system, right? So dH equals to du plus vdp plus vdv, again differentiation by parts. So again, what is dq? Again, what is du? Du from first law of thermodynamics, dq minus pdv. Substitute here, pdv gets cancelled, sdt minus tds, again dq equals pds, which is the second law of thermodynamics, minus tds. So finally we will arrive to dg equals to vdp minus sdt. Right. Now there are two types of systems. One is closed system, another is open system. So in closed system, there is no introduction of any extra quantity into the system. Right? So this is my closed system. There is no escape of matter, but here the matter can be exchanged. That's all. Now, so we have dg equals to, then you will have the change in molars or moles or the components. Right? So that's why I have to mention this term, how the free energy is going to change with the introduction of any matter into the system. Like it may be A moles or B moles. It depends. Now, what is my chemical potential? Chemical potential is nothing but the change in free energy of the system when one atom of one species is being added to the system. Right? The change in free energy when one type of species is added to the system. See, if that species, let's say that I'm adding A atoms, if I'm trying to add A atoms to the system, and let's suppose the A atoms do not interact with the system, then it is a straightforward. And if A atoms react with the system, it can be positive effect, it can have a negative effects, or it does not have negative effects. So these are the three cases. And if it does not react, then it is an ideal case. And if it reacts and it has a positive impact, then it have increase in values, or it has a negative impact, then you have a decrease in values. So it is not very straightforward. And from there we even derived, we came to this equation, and then we also even came to Gibbs-Duhem equation. After that, we derived for few samples, then we arrived to how the total free energy is related to our chemical potential. Right? So A minus xb dou g upon qx. This is the relation between the total free energy and the chemical potential of the species. Now, moving on to free energy again, then we came to how to write. Right, so how this equation equals to the slope. When you draw a tangent to any g versus x composition curve, and the intercept will give you the chemical potential. Now, how do we get that? We get it from here. Okay. Now, how do we get this one? We get it from here. Right, and how do we get this? We get it from the Gibbs-Duhem equation. That's all. After that, we came to know there are different types of solutions. One is the homogeneous solid solution, which is this one, and there is a heterogeneous solid solution. Homogeneous is nothing but the chemical homogeneity is maintained. Heterogeneous is nothing but there are two or more types of phases that's being formed. Right? It's more like a segregation of up to some extent. So that's what called as a heterogeneous solid solution. And homogeneous solid solution where everything is segregated. And again, when I mix solid 1 and solid 2, I can have two types of solid solutions. One is substitutional according to the size of the atoms, and one is the interstitial. So these are based upon the size of the atoms. Substitutional. If suppose my A and B are of similar size, and A is sitting like this in a system. If I add B, then this atom will be replaced by B. That's all. It happens when A and B are of similar size. What happens if I have smaller atoms, smaller B atoms? And this is my A, these are my A atoms. Then B atom will sit here in between A atoms because it has very small size. And we know that spheres, when are stacked together, they form voids or the empty space in between them. And that empty space is called as voids. And the smaller atoms will try to sit in those positions. See, this is a solid solution, a solvent, and we know solvent is nothing but which is in larger extent, and solid is nothing but which is in smaller extent. Again, the same, the final energy, how do we arrive? So delta G mixture is nothing but the free energy when two things are mixed. The free energy available to the surroundings when two systems are mixed. That is the delta G mix. And we came to know how the delta X mix we derived it in the statistical model, which is delta S mix equals to, if I have two atoms, then R XA ln XA plus XB ln XB. Right, and this delta X mix has two terms. One is the thermal term and another is a configurational term. And there is another term, what is the spin interaction, which we do not want to consider here, because if the thermal entropy is negligible, then this delta S mix from spins, that is even more negligible. Right, now see, this is my delta X mix, and this is how we derive for configuration entropy. So I have N NT as total number of sites, which are NA plus NB. NA is nothing but A atoms, number of A atoms, NB is nothing but number of B atoms. Right? That's all. Now here, now we have seen for regular, ideal solutions. Now what about the regular solutions, which are not ideal solutions, which we actually see in common basis? So what about the delta H mix for them? The delta H mix for them can be derived from, again, statistical model, right, or pseudo molecular model, right. And that's how we came to this point. We consider the energy of the bonds that is being formed or bonds that has been break. From there we go from before mixing to after mixing. We see either the number of atoms that's being formed and what are the atoms that's being broke, and from there we derive to delta H mix, and it has the coordination number, it has the Avogadro number, the coordination number, and then you have mole fraction of A, mole fraction of B. This is related to the probability. Yeah, this is it. Now, again, we are not considering the surface because surface has broken bonds, so let's forget about that. For now, let's suppose it is a very vast volume. Then, if the bond energy of EAB is greater than the bond energy, the modulus term, the bond energies are always negative, right? Because whenever the bond forms, there is a release in energy. Even though you need to apply energy to form a bond, once the bond forms, it releases the energy. Right. Now, if I take the modulus terms for all of this, then if EAB is greater than half of EA plus EBB, the bond energy of A and bond energy of B, then that means A prefers B around it. So that's why we have AB type of bonds, more preferable. And what about this guy? If AB bond energy is less than EA bond energy and EB bond energy, then A will try to prefer having A and B will try to be surrounded by B. They will just hate each other. So that's why you will have a segregation of one type of phase, A phase and B phase. In here you do not have any segregation because everything is get mixed up, jumbled up. Right? Now, again, delta S mix doesn't depend on temperature, but if it's multiplied by temperature, again, if something multiplied by a variable, then it will depend upon that variable, right? So if I try to increase the temperature, so this whole value goes down because it is negative value, so it will be more negative. That's what is happening here. So this tells you increase in temperature. So higher the temperature, the deeper this curves go. And I have said before, if my delta H mix becomes positive, then there will be competition between delta H mix, write it clearly, then there will be competition between delta H mix versus T delta S mix. So who will dominate first? Now at the corners, T delta S mix will dominate because at the corners when I try to do differentiation and put the value tends to 0, it will shoot to minus infinity, right? So this will dominate at the corners, no doubt. Now what about in between? In between, if it has a dominant value, delta H mix has a dominant value, then you will see a hump like this. That's what we discussed in spinodal decomposition last session, session 12. Right? So that's why we see the hump like this. If delta H mix dominates. Now, yeah, so from delta G mix, this is the final equation. You have, if it is positive, then you will have a clustering. If it is negative, you will have a complete mixing. Right? So, yeah. Now, random solution is nothing but the atoms are randomly arranged in a solution. The solid and solvents are very randomly arranged in a solution, right? Which can be seen in isomorphous phase diagrams. Right? Their atoms are very randomly arranged in that solution. Right? And isomorphous phase diagrams are also exhibited by those systems where the atoms are like chemically equal, I should say, like for example iron nickel, right? I have to see the examples, but let's say for example, let's say for brief understanding, if there are two atoms side by side, sitting side by side, let's say 22, 23 atomic number, so they are very side by side, there is only slight change in their atomic size change in their atomic mass, right? So those atoms can be easily fitted in a definite crystal structure. Even though the lattice parameter gets changed, the atomic bond lengths get differed, but still you will have that. Now, and to know the number of bonds that AB type of bonds are being preferred or AA type of bonds, we people have derived a parameter called the short range ordering parameter. So it tells you what is the number of AB type of bonds and what is the number of AB type of bonds totally random, and what are the maximum AB type of bonds that can be formed, and again number of AB bonds are random. So if PAB equals to max, then the S parameter will be 1. That means there is a perfect ordering. It is a long range ordering, right? A will be A will be followed by B, and B will be followed by A, the A will be followed by B. So there is this perfect ordering you will see, and it is a long range ordering. And if my PAB is random, then it is the short range order will be S becomes 0, the ordering parameter will be 0, then that means it is a completely random solution, right? It is a probability is half. If I take one site, what is the probability of A atom will be occupying will be half. The same goes for B. And if I take the next site, what is the probability of A occupying that site will be half. Again, same goes for B, again half. So that's what it is, completely random solution. So you cannot pinpoint and say, okay, the probability of A occupying this site is maximum. No, it is half wherever you go. So that is what we call as a random solution. And the ordered solution is something what, yeah, the probabilities are fixed. That means at one side A can be have a maximum probability of 75%, or B will have less 25%. At some side B will be have 90%, and A will have 10%. So that's what it is. So yeah, from there we derive to phase equilibria. Yeah, types of solid solutions. Then went to zeros X curves for different phase diagrams. So this is what it is, the isomorphous. Isomorphous phase diagram, right? Now yeah, so this is for isomorphic phase diagram. This is the G versus X composition. Now again, moving on to at different temperatures, we have derived for T melting point in between. So these are different things. So this is for different one, right? This is for more like a Bernoulli decomposition. So you can have a Bernoulli decomposition here. So I didn't do it for, so let's remove it. Why add something which is not right. Yeah. So yeah, this is I have alpha, and this will become alpha dash and beta. So this is how you will get that hump. And yeah, this is my tetrahedral and octahedral voids which I have discussed here. That's all. So that's about session 2. Moving on to session 3. Here I have derived the clashes, the Gibbs phase rule. Right. So what are the number of degrees of freedom? How can you know the degrees of freedom of a given phase in a system? We don't know, right? So how do we do that? This is how we do it. So F equals to, if there are C components and P phases. So if there are P phases and each one has C components, right, then it will be C into P, C cross P. Now, the first one is, so what are the variables that are being changed? One is pressure, temperature, and composition. Now, if we know the compositions of, so if I have a phase, if I know the composition of, like, if this is one phase, let's say this is P1. Now let's take black here. So let's say I have phase and I have P1 phase, and there are n components, right? So n components have n composition values. Now each component has its own composition value, right? So if I know n minus 1 of it, then I can easily tell the last one. How? The summation of the compositions, mole fractions, will be equals to 1. We all know this, right? So all I need to know is n minus 1. So that's why if I know the compositions of C minus 1, I need not to know the last one, right? So this many of terms we do not need. Now, the next one is, if my system is at equilibrium, let's suppose if I say my system is at equilibrium, then if then all the phases are at equilibrium, then their chemical potentials must be equal. So that means if I know the chemical potential of one phase, I need not to know the chemical potential of other phases, right? So that's why I multiplied C into P minus 1. So that's why I only need to know C minus 1P. I need not to know the last C and P. So minus the P minus 1 into C plus 2. Why plus 2? The pressure and temperature. That's all. Now if I simplify it, I will reach to this famous metallurgical equation, which is the Gibbs phase rule. There are other equations, but when we are dealing with physical metallurgy, right? So this is the equation that we always see when we start doing this material science. Followed by Gibbs phase rule. If I take one system, alpha phase, beta phase, if I do the dg, right, dg equals to vdp minus sdt, and if I try to equate, then I will remain with this, followed by this, dv by dt equals to delta s by delta v, and I know the delta s equals to delta s pv minus v. So if my volume change is positive, then increase in pressure will increase my temperature, or the melting temperature, boiling temperature, whatever it is. If my delta V is negative, then the increasing pressure will decrease my melting temperature, or my boiling temperature, right? So this can be seen in the water, because the volume of ice is more than the volume of water, because the ice is morely porous. So yeah. Now ice has more volume, solid volume, than the liquid. So that's why the delta V is negative here. And that's what happens in skiing. When you apply pressure, the ice starts to melt. Right, because the temperature there is freezing temperature. But when you apply pressure onto the ice with the skating, then what happens? Even though the temperature is low, the ice still melts. Why? Because the temperature is increased. The temperature is decreased, melting temperature. Right? So that's what happened. Yeah, and then I know what is my delta H. It depends upon Cp, and Cp again will have different relations depending upon your material. So this is how my equation will turn out to be if I have two cases, right? T1 and T2 temperatures. I can find different constant terms, etc. etc. So again, the G versus X composition for what is this? This is my tactic phase diagram. Please keep in mind, tick tells you there is an involvement of liquid state or a liquid phase. Toy tells me that there is an involvement of all solids. There is no liquid there. That's all. There is like a small hint. And there is also another hint, as we have discussed oxidation reduction. There is a hint called an ox red cat. So whatever the case is, either it is an electrolytic cell or electrochemical cell, if I have anode and cathode, this is my anode, this is my cathode. If it is electrolytic cell, then this is anode, this is cathode, and it is electrochemical cell, and this might be anode and this might be cathode. But whatever the case, whatever the electrode might change its state from anode to cathode, depending upon whatever cell it is. But if it is anode, it will undergo oxidation, whether it is electrochemical cell or electrolytic cell, it won't change. So anode undergoes oxidation, cathode undergoes reduction. So please keep this in mind. I hope few people know, but whoever do not know, this is one type of friend. And his Z versus X composition diagrams for this eutectic guy, right? Yeah. So that's all. See, eutectoid involves all solids, eutectic involves liquid and two types of solids, pertectic involves liquid and solid gives rise to solid. It's more like a mushy region where liquid plus solid, it has a mushy region where liquid and we call it metallurgical way, we call it as a mushy region where liquid and solid are involving, right? So they will convert into another solid, another type of solid. And there is monotectic where one type of liquid will turn into liquid. It's more or less like a liquid supersaturation, right? So yeah, you have other reactions where liquid will turn out to be liquid 1 plus liquid 2, where liquid itself is a supersaturation, right? So it's like a segregating inside liquid itself. And for example, if this liquid is not stable at that temperature, it will turn into solid. That's all. So that is what we see in monotectic reaction. It's more like a liquid reaching supersaturation, and it will segregate into two types of liquid. And one of the liquid, if the conditions are good, they will both remain as a liquid. If the conditions are worse for one type, then it will turn into a solid, and it is what we call, it is not good for both, then it will both turn into solids. So that's what we see. I shouldn't say that, but yeah, let's not go with that because it is totally violating this eutectic term, right? Now going on to this one, again we have seen this, right? It is more or less like what do you call binodal decomposition. Binodal decomposition needs nucleation and growth. Again, binodal decomposition has dou square z by dou x, double derivative of z versus x composition curve has positive value, right? That means it is a metastable. Metastable needs a solidification. Same here, z versus x compositions. We did a lot of z versus x compositions, right? So again, we did it for eutectic and we did it for pertectic also. So we did it for pertectic, right? I guess it is for pertectic. Yeah, it is for pertectic. Yeah. Lots of diagrams. Then we came to the interface effect, how the interface effect will result our z versus x, right? So, our composition. Yeah. Then we came for delta P, the excess pressure inside a spherical object or spherical system when it is inside a some system. So that's what a balloon will feel on its surface, on the surface, right? So see, I can easily show it. Let's say if this is a balloon, right? And if I try to zoom this part, this will look like this. I have an atmospheric pressure pushing this balloon from outwards, and I have, let me add different, and I have this, my bad, this is the surface, and I have this pressure with which I have filled my balloon. So this is P1 and this is P2. Now, if this guy, if this surface wants to be at equilibrium, then it should balance out this pressure, difference in pressure, right? That is the resultant pressure, right? If P1 equals to P2, then we are good. Then there will be no pressure acting on it because it is perfectly balanced, right? Times area will give me the net force, right? Now what about this net force? So if this is the balloon B is being stretched, right, in this way, So it's being stretched, that means the atoms are being in tension. So there must be a surface tension. So how do we arrive to that? We arrive to that from here. We balanced it, right? So we said this is here, this is here. We take what do you call it? We resolve, right? Depending upon theta, then we will arrive at 2t sine theta. That is my excess pressure, because T is my surface tension, right? It's not actually a force. So 2t sine theta equals to my delta P cross A. It is my force. So yeah, that's all. Then I do with what is my R, what is my area of the strip, that is R d theta. Then I do the different integration, R d theta, it will theta, then you have 2 pi r sine theta is very small, theta only gets cancelled, and 2t by r equals to delta P, that's all. Right, and this is the definition for flux of atoms, moving from one plane to another plane, right? So this is my probability of moving from one plane to another plane, this is my jump frequency, this is my number of atoms per unit area. Then from there, this is my downhill, and if my concentration grows like this, then it is an uphill diffusion. So uphill diffusion cannot be explained classically here, but it can be used with the term called chemical potential. Yeah, same. What about the second law of thermodynamics? Second law of thermodynamics tells me if my J1 and J2 are not constant, my concentration is not linear with respect to x. So that means I have some net accumulation, right? So that is what we see here. So from there we derive to Fick's second law. And again, if C is not a function, then I have a totally different one. Yeah, then this for chemical potential, and we even have the Kirkendall effect, right? Where due to difference in fluxes, the interface will move. I shouldn't say interface, but the straight line or the markings will move, right? The surface will move. It appeared to move because of the movement of atoms. This is about session 3. Moving on to session 4. Yeah, we discussed more into we dealt more about diffusion, right? So from how do we arrive at J, the fixed flux law. So this is it. Now I have again interstitial diffusion, I have substitution diffusion. So again it depends upon jump frequency and many other terms, and also the delta G value. Yeah, and we also know the substitution diffusion is very sluggish when compared to interstitial diffusion. Why? Because diffusion happens with the help of vacancy, because the atom cannot itself move inside a crowded area, right? For example, if I am in a room, I cannot just move in if the room is filled, right? I can only move if there is a space. That means there is no one. That means there is a vacancy there, so that I can accommodate myself there. So that's how even atoms can move. So that's why we have in interstitial means there are a number of voids that have been not filled, right? So yeah. Then again fixed second law. The net accumulation one, finally to fixed second law. Then we derived for simpler case where if concentration is steady state. Steady state means no dependence on time. Simple one. If I am telling steady state, then whatever the variable I take, it will not and does not depend upon time. So see, dc by dt is turned to 0, and then we directly solve it. It's a simple one. See, here's how the equation will come. Now the interfaces, a boundary between two mediums. See, for liquids, the surface energy and surface tension are equal, because if I disturb the surface of the liquid, it will accommodate itself, because the atoms are in continuous movement inside the liquid, but it is not the case for solid, right? So that's why we take mostly the surface energy for solids, not surface tension. Yeah. Again, the free energy of a surface if the surface is being cut, right? So this is how it looks, and we derived for this one from this. What is the surface energy of 100 surface of a simple cubic one? We have assumed the basic assumptions. From there, we derived how the surface energy will change with respect to the theta, right? This angle of rotation, this cutting angle. So if I draw that, then it will form equilibrium surface. First it will form a net, and from the net we will have an equilibrium surface, and this net is called as Wolf net, right? So this is how we derived from it. Any equilibrium system tries to maintain an equilibrium shape, that it must satisfy. Any equilibrium system tries to maintain an equilibrium state or a shape, with a shape, then it must satisfy this one. The surface energy times its area must be equals to minimum. The summation of all the surface energies times the areas of the surface must be equals to minimum. Then only the total surface energy total free energy will be minimum, right? Because the G is equals to G naught, which is the volumetric term, plus A times surface energy. So if you want this to be minimum, then this to be negative, and this should be have minimum positive value, because this term cannot be negative, right? Because the surface energy is being created by breaking bonds. And the interfaces, interface effect, and we have, for example, we have two types of grains inside the system, and how these grains are aligned with each other. They can have a, there are two types. One is a tilt, other is twist. So tilt boundaries and twist boundaries are dependent or explained upon how the surfaces of the grains are rotated with respect to each other, right? So in tilt, this is my boundary plane and my rotation axis. So boundary plane and rotation axis are parallel. So this is my boundary plane and this is my rotation axis. They are parallel. And if this is my boundary plane and this is my rotation axis, this is perpendicular, then it is a twist. And in tilt boundary, we have low angle tilt boundary, we have high angle tilt boundaries, right? So low angle tilt boundaries can be easily accommodated by dislocations, and high angle tilt boundaries cannot be accommodated by dislocations. By dislocations, core will overlap. And why they will cannot be overlap? See, why they cannot be accommodated? Because dislocations have their own strain fields, and it's like a magnet. When two dislocations came close to each other, they try to repel, because the strain fields among them are positive. Same goes for charges. If you have positive charge, they will repel. Same goes for two same type of dislocations. Right? If they have positive negative dislocations, then they will annihilate each other. They will combine, and you have nothing there. Right? So yeah, here you go. There are dislocations here. And the twist boundary is a little bit complicated, because you have cross grid screw of dislocations, right? The twist boundary is always complicated to understand. Yeah, so this is my surface energy, and with respect to the theta, so this is the regime of 10 to 15 degrees. After that I have a high angle grain boundary, so this surface energy will remain constant. And I have special high angle grain boundaries, which are twin boundaries, where there is a plane across which the distribution of atoms looks similar, right? So that is why called as a twin boundary. So here and here they have same oriented distribution, right? That's why we call a special angle twin boundaries, or special angle high boundaries called as a high angle boundaries or called as a twin boundaries. Right. So the gamma will dip at a certain angle of rotation. So yeah, then we arrive to coherent surfaces, coherent interfaces. So coherent interfaces are nothing but if the lattice parameter is same on both sides, right? And this is also coherent interface where there is a perfect matching of one-to-one matching between atoms A and B. Even though the lattice parameter is different, the planes try to accommodate by straining themselves. So see, here it can be perfectly matched. Here, with respect to one rotation of B atomic planes, they are matched, but here it is not the case. They are strained atomic planes, and because of this, you will have the extra term, the strain energy, adding to the system. Right. Now, for the total energy of the system, you have volumetric free energy, I have surface energy, and I have strain energy. That's all. Then again, this is the and for semi-coherent interfaces, to accommodate the one-to-one match, there are introduction of dislocations, and that means at one point there is no matching between these two planes. That's all. So this is my semi-coherent interface. Looks like this. Moving on to, yeah, you can define different types of parameters here, right? So the lattice mishap, the lattice mismatch parameter, different things. The distance between the dislocations can be derived from it, which I have derived here. And I have incoherent interfaces, then the surface energies of 11110, 11120, the same as I have done before. When I have a surface and it's been cut like this, then it is this surface will have 100 surface energy. If it is cut like this, what should I say? This was the 111 type, so it depends. And see, I have mentioned here how to calculate these values. Yeah, that is about session 4. Moving on to session 5. Here again we have discussed the coincidence lattice sites. If two lattice sites are superimposed and they are rotated with respect to one axis, then at some places there will be one-to-one matching between the atoms of two different species, and some places there might be not. So that is what we call as coincident lattice sites, and we even represent with it some coincidence lattice density to know what is the density of atoms that has been perfectly matched. Right. And then yeah, you have these vectors that's being rotated. What should be the rotation and all. So yeah, this is for equations for them, right? Here again the same. Again. Now, finally to the nucleation. What is nucleation? Nucleation is a formation of a new phase. Right. So from delta G we had, if something is formed, we have the volumetric free energy, which is coming from one phase has formed from another phase. Right, and the next one is my surface energy, which is coming from the interfaces, which we have discussed in previous 2, 3, 4 sessions, right? And then I have the strain energy, which is also mentioned there. Right, this is my total strain energy. Now, how much is this? That's what we are going to calculate here. Now again, what is manipulation? Formation of a new phase from the parent phase, which is distinct, right? And there are different types of, and one is the solidification, is the formation of solid phase from liquid phase. And nucleation can happen in solid phases also. It shouldn't, I shouldn't say it is only for like liquid, like solidification. It can be seen for different phases, like not only for liquids, we can even see them for solids also. Now, right. So we used the equations, the G1 minus G2, that means the free energy of solid minus free energy of liquid. Right. Now, the delta G equals to delta H minus T delta S. This is a famous equation. We know that, right? Now, so moving on to this, right? So delta G will be equals to delta H minus T delta S. Now, if a phase transform, let's suppose I have solid here and liquid, suppose I have liquid and small phase of solid forms, then my G1 will be, initially it is volume of solid plus volume of liquid. Again, it is, we are considering how should I say, there is no volume change in between solid and liquid. So whenever a solid is forming here, that means there is no volume change, right? So that's what we see. Here I should mention Vs equals to Vl. The delta V is 0. So please keep in mind that there is no volume expansion or contraction when solid is formed, which is not an ideal case, but still for simplicity, for mathematical simplicity, we are considering Vs equals to Vl. So from there I write it as G2 minus G1, which will have Gs minus Gl. Obvious, the free energy of solid minus free energy of liquid. Then I have variable term, As minus gamma S. So I know my V equals to volume of sphere 4 by 3 pi r cube, and A is my 4 pi r square. So delta G will be equals to delta H minus T delta S. And delta H, how do we derive? See, the Gs equals to Hs minus Tms. Again, Gl will be H minus Tms. Now at equilibrium, Gs equals to Gl. So that's why we did here, and then equated, it will be 0. So Hs minus Hl equals to Tm times Sl minus Sl. So delta H equals to Tm delta Sl. So that's why I wrote it here, Tm delta S. So I take delta S as a common. Then again, delta H, what is delta S? Delta S will equals to delta H by Tm. Right. So I substitute my delta H value, delta H by Tm. This is the Tm minus T, and this delta T, Tm minus T, actual temperature, will be equals to undercooling. So how much undercooled we are, under the melting point we are.
So undercooling is nothing but how much undercooled, or how much, what is the temperature that we have been cooled from, that we have cooled from the melting temperature, right? So that is my undercooling. Now the next one is how, what is my critical radius, and because there is a term, let's substitute these terms here. So I will end up with the delta G in terms of R. Now, what if I do the differentiation? If I do the differentiation, then I will remain with this one. Two cases. Two critical cases. One, R equals to 0, which is okay when there is nothing formed. Everything is 0. There is no change in free energy. And another thing, when I have R star will be equals to 2 gamma S L by delta CV. At that point, the free energy, total free energy, is approaching to 0. That means this guy is equals to this guy, more or less. Or this guy is more like dominating. Right? So that is what it is. That means the free energy will not change if I add small radius. The change of, there is no change here. That is what we are going to do. Now, from there we derive the R star, which is our famous relation. It should be written in modulus, right? Because the delta GV is negative term, and R star and this gamma SL is our positive term. So negative, positive will be negative. So our R star, which is a physical quantity, physical quantities are measurable physically. So we cannot measure negative terms, right? So that's why we keep it the modulus here, or for simplicity we can even mention minus here if you do not want to keep the modulus there. Then I substitute here, then I will have this delta G star, which is nothing but this value. After that, yeah, then we only derive it for sphere. We can even derive it for a cube. We can even derive it for a cylinder. We can derive it for any shape, any physical shape, right? So yeah, I mean physical geometrical simple shapes, or like, I shouldn't say the pentagon or hexagonal shapes, right? Or buckyballs. Like, we cannot physically do the volume part, right? It is, we can do it, but it is not very straightforward. See, this is a star for the cube, and this one is yeah, this is the number of, there shouldn't be star here. It is more like the number of nucleations that has been formed. Only the number of nuclears, right? The number of nuclei that's been formed. That has been formed, and this is the total number of sites. And multiplied by jump frequency of atom from from liquid surface to solid surface. This is given by this. Times will give you the rate of homogenization, right? And I have this one, and then I have heterogeneous nucleation. How the heterogeneous nucleation happens? So heterogeneous nucleation is more preferred than homogeneous nucleation. I even have explained in previous session 12. So because of the interface effects. So in heterogeneous nucleation, I have given a total lecture for this, I guess. Yeah, I have derived everything here. So I took a cap, and then I took a thin strip. Then I started doing right? So A equals to 2 pi r times dr thickness. So I'll explain this. So if this is my strip, this is the strip I'm talking about. So A equals to 2 pi r cross dr, right? So what is my r? R equals to r sin theta. Why? If this is my r and this is my capital R, then sin theta will be equals to opposite side by hypotenuse. So r equals to sin theta will be opposite side by hypotenuse. So r is r sin theta. And then dr. So dr will be strip length. And what is the strip length? And we know if I have a small arc, then theta will be equals to arc length upon radius. Now same thing you have done here. So dr will be equals to r d theta. Right, now if I multiply this, then I have 2 pi r square sin theta d theta, and if I do that, this is dA. And if I do the integration, it will be 2 pi r square sin d theta. So integral of sin theta d theta will be cos theta. So fine, substitute 0 to theta, and there is a minus, so the upper limit can be exchanged. And finally, if I substitute, I will arrive at 2 pi r square 1 minus cos theta. Now what about the volume? Volume can be given by 2 pi r square cross thickness dt, right? Write this part. Yeah. So it will be volume dV will be equals to 2 pi r square dt, which is thickness. So this is my thickness. I want to know this. I know this dr. I want to know d theta. So if this is theta, then it will also be a theta. Right. If we do the simple geometrical thing, then it will become theta. It will be 90 minus theta, and because this is 90, this will be theta. Right. Why? Because sum of angles in a triangle are 180. So 180, and if this is 90, so half 90 goes here, then theta 1 plus theta 2 must be equals to 90. If one is theta 1, theta, then another should be 90 minus theta. So that's how we arrive at this. From there, I have written for, this is more complex, for clear understanding, I have done this stage. So our theta 3 will be finally, it's not d theta, it's theta. So it is theta. So dt will be equals to again sin theta will be equals to dr opposite side upon hypotenuse. So dt equals to dr sin theta. Substitute by r square sin square theta dr sin theta. Then again pi r square sin square theta r d theta. Again dr will be equals to sin theta d theta. R d theta, sorry. So finally I have pi r cube sin cube theta d theta. Again, we have an integral here. So how do we do that? So we can form the UV form, right? You can use UDV form. So integral of UDV will be equals to UV minus integral of V. So V equals to minus cos x. U equals to this much. I do the integration. This will come out, and I have remained with this guy. So du equals to minus 1 sine power n minus 1 minus 1 or minus 2 x cos x dx. So minus of integral minus cos x n minus 2 sine power n minus 1 cos x dx. And I'll come to this. I know cos square x is equal to sin square x. So we'll substitute here. Then I have everything in terms of sine because we do not want cos here. So everything I have sine terms. So I shift this one here. So it will be cancelled. So everything will be divided by n. So this is the final relation. Now integral of sine cube x will be equals to minus 1 by 3 sine square x cos x plus 2 by 3 sine x dx. Sine x dx will be cos x again. So that's all. Finally I have arrived to this equation. Now for simplicity I am going to multiply 4 divided by 4 so that it will become 4 by 3 pi r cube. Right. This is here also. So and this term will become f of theta. So that's why I have mentioned in previous class also f of theta will be 2 minus 3 cos theta plus cos theta 4. Right. Moving on to delta G will be heterogeneous. So if I take f of theta as common or t theta as common, delta theta is common, then y will be equals to 2 minus t3 cos 3x by 4. So if you want to know maximum value will be 0, maximum value will be 1, smallest value will be 0. From there I have finally reached to this equation y delta G homogeneous is less when compared to delta G, so heterogeneous is less when compared to delta G homogeneous. Then again these are our relations. So this is for the minimum critical values, right? The small and larger values. Then again I have cos theta values. We have plus 1 or minus 1. If I have 1 and theta can be 0, so cos theta will be 1. If I have minus 1, cos theta minus 1, cos theta minus 180. Or can I have 360. Right? Now moving on to the next part. So minima f of theta equals to 0, maxima f of theta equals to 1. So minima is nothing but this theta is equals to 0, right? This is what we see here. This theta will be 0, and that means there is a completely weighting of the surface. If the theta equals to 180, that means this surface is perfectly standing on it, right? Yeah, and this is 0, delta G homogeneous, delta G homogeneous. These were simply mathematical terms. Now moving on to session 6. And here we started with heterogeneous nucleation again. So few things to be told here. So this is our governing relation there. Again the cap model. Yeah, again the same, the derivation part. Then I have a final volumetric term, followed by the delta GR term. So again the same here. So this is our critical radius for any type of nucleation, whether you take homogeneous or heterogeneous. Right. So there are caps. The cap model again. If they have two caps, then what is delta G? Right. Delta G and those terms. Again, see here, 2 times of theta. That's all. The times will increase. That's all. So this is for delta G homogeneous, delta G heterogeneous, for gamma alpha alpha and gamma alpha beta. And these are the rates of nucleation. The heterogeneous nuclides. The heterogeneous nucleation requires less ample cooling because of this of theta term. Right. And this is my solid liquid interface motion. And again, what are the types of interfaces? Right. I can have smooth interface, I can have rough interface. So rough interface is like this, atomistically rough. That means there's a diffused interface. Smooth interface means there is atomistically smooth. Right. This is an atomistically smooth interface. Now which is not here. This is atomistically smooth. And this is rough. Then, and this is the diffusion between them. Right. This is the whole diffusion part for the atomic jump. Right. And this is also the movement of that interface. This interface. Right. This interface movement given by this velocity. So yeah. And this smooth interface, which is seen in the semi-metals, right, or the metalloids and non-metals. And again, how the growth rate is changed with the intercooling. So this is the growth for thermal dendrites. So for example, if I have solid and liquid interface, and if my temperature is being drawn from liquid to solid like this is less temperature, this is the melting temperature, this is again in liquid have a high temperature. So heat is being drawn from liquid to solid, from solid to the surroundings. So this is how the heat is being drawn. Then this is how my surface will grow. So it is given by this. This is the velocity of the flight. Now if what happens my thermal or my temperature gradient is a negative inside the liquid. Right. If my thermal temperature gradient is negative in the liquid, then I have unstable interface. There will be no flat surface. The surface will grow like this. Right. So that's we called as a cellular growth. And we also known as it happens in pyrolysis, and it is also known as thermal dendrites. Then again the growth equation for that also. So I have to write few things here which can be easily done. So this is our final velocity relation. Now what happens if we have an alloy? Then that thing we called as constitutional diffusion, constitutional intercooling. Right. One is thermal dendrites,
The other type of dendrites we see in solute atoms or in alloys is known as a constitutional undercooling. So from that we even discussed the coring, which is the compositional change upon cooling. Right. Moving on to session 7. So I have discussed few things, liquid to solid solidification here. Then we move on to supersaturation. Supersaturation, again I have mentioned many times, supersaturation is nothing but reaching beyond the saturation limit of any type of species in a solution. That is supersaturation, right? Now, and that is how we came to this coring part, followed by I guess this is this is Thailand rule, right? And then we have alloy solidification. In alloy solidification, what are the assumptions we take? Complete mixing, or there is no diffusion of solid. From there we obtain the Scheide equation. And the other one, which is the diffusion in solid, which is there is no diffusion in solid, and liquid we are assuming only concentration gradient. It is dealing with the stagnant liquids or stagnant melt pool that are being solidified. So this is how our relation looks like. Yeah, again the constitutional supercooling, right? So this is my thermal gradient inside the liquid, and this is my equilibrium solidus line, equilibrium temperature line of a solidus equilibrium temperature of a solidus line. So the constitutional undercooling will happen only if my actual thermal gradient is below of my constitutional, all my solidus temperature line, right? So then only I have a solidification happens. So yeah, and there is this heat drawing effect, and then some more explanation on that. So this is the relation, right? This is the relation to happen. You have planar interface. If this is the condition, you will have dendrites in columnar regions if you have this condition. So yeah, there are primary dendrites, secondary dendrites, and tertiary dendrites. And this is the eutectic solidification. Yeah, the free energy composition diagrams. So in eutectic, so this is one famous one, which is the pearlite formation, where this is the one eutectite type of transformation where solid alpha will turn into beta plus gamma. So that means the gamma austenite is turning into alpha Fe. So we take red one. So gamma Fe will turn into alpha Fe plus. It is what it means. And from where we derived from the critical radius part. From there we use that part to columnar one also. You can see these things here, and this is the reason why these columnars will look like this jagged surface. Why they cannot have a flat surface like this? Why you have a jagged surface like this, right? So this is the reason why, because of the surface energy. To minimize the surface energy, if I have flat surface, then this surface energy is not balanced. So that's why it forms a lock like this. So that's all. And then we have the delta G, these relations where if I have the infinite length, right? So the distance, like the cellular parameter. What is the length of cellular parameter? What if it is infinite, and what if it is some constant value? How the delta G terms will change. So this is how it will change. And then the rate of solidification will depend upon the diffusion of atoms on the interface. Again, how do we derive velocity different value? Other equation. So then I have the precipitation reaction, right? Then we have the most famously the precipitation hardening, which is mostly done in supersaturated solid solutions, right? So that's all. Coming to session 8. See, we started with different types of phase transformations, and in phase transformation we have diffusional phase transformation, and also we have diffusionless phase transformation, right? So in diffusional transformation I have this protectoid, diffusional transformation, protectoid, monotectic, it is protectoid itself. Now protectoid phase transformation we have mostly discussed, and there is also the ordered disordered phase transformation, right? So there is also an ordered disordered phase transformation. There is also this massive phase transformation. Right, massive phase transformation. There is this change in phase, but the only change is the crystal structure, but no composition change, right? And then we have phase transformations depending upon temperature and diffusion, right? And how the nucleation and growth are being affected, right, with the undercooling. I have mentioned before that diffusion requires the temperature, and the nucleation requires the diffusion requires the high temperature, and nucleation requires the less temperature, right? That means the higher undercooling, the higher will be the nucleation. The higher the undercooling, lower the temperature, lower the operating temperature, the sluggish will be the diffusion. So there is always a competition between the diffusion and, let's take a red one. There is always this competition. Let's erase this part. There is always this competition between diffusion and the nucleation rate, right? So there is also this combination between the diffusion and nucleation rate. So that's how we achieve this optimum value at a certain temperature. Right? Now this is for critical radius. Again, how this R will depend upon the strain energy, how this R star will change with respect to the undercooling, and the nucleation rate also being derived here, right? Then I have how the diffusion is going to affect with the temperature, then how this precipitate will grow, that is also has been derived here. It's nothing but velocity is given by dx by dt, and the flux will be equals to minus g dv dc by dx. So this can, the flux we know, the flux will be equals to velocity of the fund minus times the concentration difference, right? So this taken here, and then finally we'll have the velocity fund followed by our final one, followed by the TTT curves, TTT and CCT. So TTT is nothing but time temperature transformation curves, and CCT are nothing but continuous cooling transformation curves. Now these TTT diagrams are obtained by the amount of, it is plotting by two graphs. TTT curves are plotted to form two graphs. One, how
the fraction of phase is formed versus temperature. The next one is the start versus temperature versus time. Sorry, at a given temperature, what is my start time? What is my finish time? Right. So phase transformation start time, phase transformation finish time. From these two curves, I will obtain the TTT curve. So this is how it is. Right. Now, moving on to the precipitation hardening. Right. I have precipitates forming. At first, you have GP zones, then I have theta prime, then I have theta double prime, then I have theta. So, moving from GP zones to theta double prime, theta prime, theta. What is happening? The matching is changing. That means the matching between the atoms of parent matrix and the precipitate matrix is continuously changing. The atomic one-on-one matching. Right, and the lattice parameter and the shape also is being changed. Why it is happening? It is happening because the system cannot accommodate the drastic change in energy. Right, just like I've said before, the whatever solidification that is being happened, it is a metastable state. So if a phase tries to transfer from one phase to another phase to solidification, it needs to be applied with some energy such that it can escape that metastable phase and form a stable phase. So that's why the solidification itself is a process by which the metastable phase is converted into more stable phase. Right, so it should be kept in mind. Now, so this is how the free energy is going to slowly decrease to the final value. Yeah. So that, and again, how the precipitation hardening takes place, because the dislocation will try, if the precipitate is too large, the dislocation, if the precipitate is small, the dislocation will try to correct it. If the precipitation is too large, the dislocation will take a bow around it and it will move. This is called as the Orban mechanism, right? And for the dislocation to bow, to change its to change its direction, it needs to undergo, it needs some energy. And if there are more number of precipitates, the more energy is required, and the more the dislocation needs to bow around these precipitates, right? So it has higher toughness when compared to this guy. Now, how, again, I have mentioned before, how diffusion versus temperature and nucleation versus temperature is playing role in these two graphs. Right? I have mentioned that before, and again, TTT goes for this precipitation hardening, and I have phase transformation for retrograde transformation. Again, transformation happens only at grain boundaries. That's all. Moving on to session 9. So transformations, again, retrograde transformation happens at grain boundary. Why grain boundary? Because grain boundary has better free energy. Right, we can minimize the free energy. So again, how the TTT diagrams and retrograde transformation, how they grow, and this is about TTT diagrams. So how TTT diagrams are made, and this is for how undercooling defines the morphological structure of our grains, whether we are forming coarse or fine. So this is how it is formed, and there is also this term, the Benedict transformations, so which happens when the diffusion of iron or carbon atoms are being sluggish. So yeah, this is our Benedict structure. This is our upper Benedict and this is our lower Benedict. So it looks like a leaf-like structure. and then I have the diffusionless transformation, right, which is happening by a certain movement of planes, right. Right, it is accommodated by the certain movement of atomic planes or twin boundaries, right. These my TTT curves for austenitic phase transformation, and these for matacetic phase transformations. Right, the diffusionless smooth phase transformation where the atomic planes are being moved, right, collective movement of atomic planes. So this is about session 9. Coming to session 10. Again, we did some pieces of detector transformation, and then we had CCT curves for Benedict transformations, and then bits and pieces we have discussed about Materials-ME phase transformation. It's all about Materials-ME phase transformation, and then we are talking about this. The order, it's not an order to order, it is a massive transformation. We discussed more about the massive transformation and also how the temperature affects our diffusion and nucleation rate. Again, phase transformations and massive transformations. See, the precipitation takes place, and the massive transformation is a bit different because in massive transformations, the atoms will try to move from one phase to another phase, right? From phase 1 to phase 2. No, it will not happen. The thing that happens is only the atoms at the grain boundaries will try to arrange themselves. So the boundary will move. So the grain boundary will move. So that is what happens here. The atoms will try to arrange it themselves at the grain boundaries. So that is why the massive transformation happens. And whoever shows the Materials-ME transformation, they will show the massive transformation. Because in the Materials-ME transformation also, there is a collective movement of only few atomic planes. That means at the grain boundary also there is movement of atomic planes, right? Atomic position movements. The distribution of atomic atoms at the grain boundaries. So that is one hint case. And yeah, you can see this, the grain boundary starts to move in. This is for the massive transformation, and these are the G versus X composition curves for the massive transformation, when they are going to happen. Right, so you can see this is the G massive and this is the G precipitate. So they can stop at here. They can stop at this point. And this is the minimum energy. They do not have to come to the farther point. Right. Now, it happens in copper aluminum phase transformations, and you can see in massive transformation the temperature, the cooling rate. This is the cooling rate we need for the massive transformation. It's not too low or it's not too high like Materials-ME transformation, it's in between. Now, order to disorder transformations. Again, the atom will try to arrange themselves in these order to disorder transformations. Yeah, that's all. And then finally we came to the spinodal decomposition. To session 11. In session 11 we have seen two types of phase transformations, special phase transformations, the binodal phase transformation. I have binodal phase transformation, which is this part, and I have spinodal phase transformation. See, I have discussed this briefly in two sessions, session 11 and session 12. So this is about this one. Again, how the transformation happens. If there is some composition fluctuation, this fluctuation will grow and become like this. In spinodal decomposition, you do not need you do not need nucleation because it happens spontaneously. So these are the diagrams they look like, and this is our phase transformation via toughening in materials, in most of the ductile materials. So where we do the cold work, we increase the strength of the material, and then when we try to increase the temperature, it will undergo strain-free transformations. That's why the strain-free grains form. So that's what happens. At first we do the deform, the dislocations will accommodate themselves. So this is how they accommodate, and they form the polygonal structures from which you have strain-free grains, and they will grow. So, and there is a temperature regime also, right? So there is also the temperature regime where it is 0.3 to 0.5, which is a warm working. This is from above 0.5, which is a hot deformation. This is warm deformation. Below 0.3, which is cold deformation. A cold work, warm working, or hot working. That's all. So that's what we have discussed here. Finally, moving to our final session, which is our session 12. So we extensively discussed spinodal, binodal, and what do you call coherent spinodal decomposition. So I'm not going to discuss these things because I have discussed briefly in session 12. So from there we defined why this hump is coming. So from there we derived why this hump came, and then why this segregation happens, how the double derivative terms define where the composition point there and which level of phase transformation happens. If it is positive, then we need it is a metastable state. So to come to more from metastable state to final more stable state, we need to have nucleation. And if it is negative, we have a spinodal decomposition. Right. So after that, so this is how the compositional changes happens here, and this is the nucleation part. So these are the different terms of spinodal decomposition, and if we do not have this part, the surface energy part, then there is no surface. That means everything is coherent, and if to achieve coherent, if there is some mismatch, then you will have a strain. So that's why I have mentioned strain here. So that's why we call it as a coherent spinodal decomposition. That's all. And then we have toughening. This is again a spinodal decomposition. We see it by BSc, and then the precipitation, the retrograde solidification, which is normally seen, and then we have cellular precipitation, where the boundary itself moves in the precipitation, right? And then finally, and again, the boundary movement will depend upon two types of diffusion: diffusion through the lattice ahead of the advancing cell front, or diffusion through the moving boundary itself. Right. So they have two cases, and then I have said the retrograde phase transformation, and the last one is the ceramics. The transformation to toughening. So we do the transformation and we do the toughening. In ceramics, the dislocation motion is very complex. So we mainly worry about the crack propagation. The crack propagation can be done by the diverting of that crack, or the application of a compressive stress, which can lead to the diminishing of crack propagation. So for crack to propagate, these walls to be in tensile, but if we compress them, then the crack cannot grow. So this is all about a brief recap about sessions. So this is our final session in phase transformation materials. I hope this is helpful for you guys, and if you have any doubts, again, my mail is open, and also the YouTube comments are there for you. You can comment there. I can reply you as soon as I can. So, and also your exams are coming, so please study for them. I know you will study. So thank you for your patience.
And yeah, I hope if this course rerun again, I will take this course again, as again the same TA, PMR TA as code clarification. So I hope we will meet there again. And thank you. Also, all the best for your exams. So if you have doubts, you can stay and ask here, and if you do not, you can leave.